Section 4.4, Graphing with Calculus and Calculators. The method we used to sketch curves in a preceding section was a culmination of much of our study of differential calculus. The graph was the final object that we produced. In this section, our point of view is completely different. Here we start with the graph produced by a graphing calculator or computer, and then we refine it. We use calculus to determine or to make sure that we reveal all the important aspects of the curve. And with the use of graphing devices, we can tackle curves that would be far too complicated to consider without technology. The theme is the interaction between calculus and calculators. So for example 1, we wanted discovering the hidden behavior. So we want to be able to graph the polynomial f of x, which is equal to 2x to the 6th plus 3x to the 5th plus 3x cubed minus 2x squared. We're going to use the graphs of the first derivative and the second derivative to estimate all the maximum and minimum points and intervals of concavity. So let's go ahead and graph this. So I'm going to go ahead and post here our graph. So I went ahead and graphed this on Desmos, which you can do. Okay, so I want you to first look at the first graph here, number 1. Okay, what I did is I put the function into Desmos, and we can see here that we get this graph where the x-axis in the viewing rectangle is between -5 and 5, and from -1,000 to 41,000. Now this viewing rectangle is useful for showing that the asymptotic behavior or the end behavior is the same as for the function of y is just equal to 2x to the 6th. But it is obviously hiding some finer detail. So we want to change it to the viewing rectangle in number 2. So we're going to go from -3 to 2 and then from -50 to 100. So here is our function. Now what we can see here is that from this graph, it appears that there is an absolute minimum at about -15.333 when x is approximately -1.62. So there is our absolute minimum. Okay, and we also know that it is decreasing from -infinity to -1.6. So it's decreasing from here to there, which is -1.6. So we can see that it's decreasing. Okay, and where is it increasing? Well, it's increasing. So there we know the function is decreasing on that interval. And we know it's increasing on the interval from -1.62 to infinity. So here we see it's going to be increasing from here to infinity. So we can see that the graph is increasing here. Okay, now there also appears to be a horizontal tangent at the origin and inflection points when x is equal to 0. And when x is somewhere in between -2 and +1. So over here at 0, we can see it flattens out, which tells us that there's an inflection point there. And when x is in between -2 and 1, because it is changing from decreasing to increasing here. Okay, so now what we want to do is we want to take this function, and now what we want to do is be able to find the first derivative and the second derivative. So we're going to find f prime of x, which is equal to 12x to the 5th plus 15x to the 4th plus 9x squared minus 4x. And then we want to also find the second derivative of this function. So the second derivative is going to give us 60x to the 4th plus 60x cubed plus 18x minus 4. Okay, so now let's go ahead and graph the first derivative, and we're going to use Desmos there. And we're also going to graph the function again and zoom in on a little bit more. So here on Desmos, okay, I've graphed the function, which is number 3, which is the derivative function. So this is the derivative function. And when we graph the derivative, we see that it changes from negative to positive when x is equal to -0.162. So let's go ahead and take a look at that. So it's negative here, and then positive here at negative 1.62. Okay, and this confirms that by the first derivative test that the minimum value that we found earlier. Now, but perhaps to our surprise, we also notice that the first derivative changes from positive to negative when x is equal to 0. So we can see here that it's changing. So here it is positive, it's above the x-axis, and then it becomes negative here, okay, which is below the x-axis. So that means at 0, it's changing from positive to negative. And then it's going to go from negative to positive when x is equal to negative 0.35. So again, let's take a look at these values here. So we can see here that there are changes. So here at negative 1.6, we know it's changing from negative to positive. And then at 0, it's going from positive to negative. And then at 0.35, it's going from negative to positive. So again, let me go ahead and just write that sign down here. So here, it's going from negative to positive. And then from here, it's going from positive and then to negative at 0. And then at 0.35, it's going from negative and then to positive. Okay, so this means that f has a local maximum at 0. So there's a local maximum at 0. And there's a local minimum at x is equal to 0.35. But these were hidden in the second graph. Now, indeed, if we now zoom in towards the origin, which is graph number 4 of the fourth graph, we see what we missed before. There is a local maximum value. So let's take a look at that local maximum value. We have a local maximum value of 0 when x is equal to 0. So there is the local maximum. Okay, and then we also have a local minimum value at about negative 0.1 when x is approximately negative or 0.35. Okay, now let's talk about concavity. So if we want to talk about concavity, we need to look at the second derivative. So let's take a look at the graph of the second derivative. Okay, so we also, what about concavity and the inflection points? So from the second and the fourth graphs, there appear to be inflection points when x is a little to the left of negative 1. So over here, we can see here, down here, because I wanted to make sure you can see this graph. So here, this is the graph of f of x, and we can see that to the left of negative 1, there is an inflection point. There appears to be an inflection point. And when x is a little to the right of 0, okay, there is also another inflection point. But from that graph, or those graphs, it's difficult to determine inflection points from the graph of just a regular function. So in order for us to be able to identify, we need to graph the second derivative as we did here in graph number 5. Okay, so the next thing we need to do is we need to determine, okay, what's happening from the derivative where it's changing from positive to negative. So if you take a look at where x is equal to negative 1.233. Okay, so here it is positive, right? And then it's turning to negative below that point. So therefore, there is where it's negative. Okay, and we can also see that it's going from negative to positive. So here it's going to negative and then to positive at the value of x of 0.193. So it's going from negative to positive there, and we know it's going from positive to negative from the value of negative 1.23. Now, so therefore that tells us that correct to 2 decimal places, it's going to tell us that f is going to be concave upward on negative infinity to negative 1.23, so it's concave upward here. Okay, and it's also concave upward from 0.19 to positive infinity. And you can see that over here, that it's concave up here, and then from here it's also concave up. And then we know that it's concave down from negative 1.23 to 0.19. So we can see here that between these 2 points, it's going to be concave down. And if you look here, it's concave down here because it's concave down on that graph. Okay, whereas we can see that it's concave up from negative infinity to negative 1.23, and we can see that it's concave up from the value of 0.19 to 0.058. Okay, and then there are also inflection points that we need to consider here. So when it's changing, we know from positive to negative, that means that we have inflection points here and then inflection points here. So we have an inflection point here, and there's the other inflection point, because if we put in f of negative 1.23, then we get an output of negative 5.59. And if we put in the input of 0.19, then what we get is an output of negative 0.15. And so therefore we can see that that's going to give us our inflection points. Let me correct this here. So that should be negative 0.06, 0.06, which means that the output here for this inflection point is 0.06. And so what we have discovered is that there is no single graph that reveals all of the important features of this polynomial, but graphs 2 and 4, when taken together, do provide a more accurate picture.